So let me record. Okay. So uh, welcome everyone. We are pleased to have Professor Sandeep Juneja from TIFR, and he will be talking today on partition identification for heavy tail distribution using multi-arm bandits. So over to you, Sandeep.
Thank you, Ketan. Thank you for this invitation. So yeah, so I've started giving talks using a tablet. So it's a new experience, but we attempt to make up for the fact that it's not a live talk. So this is joint work now with Subhashini. Uh, she was a postdoc here, and then Shubhadda, who's doing a PhD with me right now. And some parts are with Wouter Kuhlen, who's in CWI. So this is some of the tail distribution work, which I'll talk about towards the end. All right. Okay, so what is the problem at hand? So finding the correct partition set containing given vector of distributions. So we'll start by given a vector of distribution. Think of these as k arms, k probability distributions, right? We don't know these distributions. We can sample from each one of them. We can sequentially ask, okay, let me sample from arm 1, arm k, arm I, so on and so forth. We generate independent samples, and we are given this universe Q, which is a collection of such arms, such vector probability distributions. And this universe is partitioned into P subsets, A1, A through to AP. So given nu in Q, so this we know that nu comes from this family Q, that we know. We need to come up with a delta correct algorithm that finds the AI that the nu belongs to. So nu belongs to this vector of distributions belong to one of these AIs, and we need to sample from these arms and come up with a deduction that it belongs to a particular AI. And we want to be correct with probability 1 minus delta. Delta is specified to us upfront, right? Somebody tells us you are allowed 1% error or 0.5% error. That's upfront specified. So now we want to do this as quickly as possible, right? With as few draws of arms as possible. How do we do that? That's the question we're answering today. So is this clear? This is kind of an abstraction of a lot of bandit problems. These are kind of best arm identification problems. There are a lot of them. So this was an abstraction to kind of capture them in a unifying framework. So any doubts so far? We
That is
know
clear, but like on what basis the algorithm will decide AI?
it will look at the samples, and based on the sample, it's going to decide. Just purely data driven.
Okay.
It's purely data driven. Yeah. So that's the whole point. How far can we push this? Right. And the primary example to keep in mind is finding the distribution or the best arm with the largest mean. So I give you these k distributions, and I ask you sample from these k distributions as much as you want. Pick whichever arm you want to sample from. At the end of it, tell me which arm has the largest mean. Right? So that's a classical question. Best arm identification. So then A1, this AI becomes okay. These are all the vectors of probability distributions where the ith arm has the largest mean. A1 becomes the all these vector distributions where the first arm has the largest mean and so forth. So now you're given a vector and you want to find out whether it belongs to A1 or A2 or AK, so on and so forth. So best arm fits into this framework, but you can now imagine many things, right? If you want to find, let's say, the best three arms, uh, which are the three arms with the largest means, or pretty much anything, which arm has the largest median, or which few arms have lie in the middle in terms of median values. So pretty much anything you can think of comes into this partition framework. Later we'll talk about, okay, let's go beyond means and let's look at value at risk, quantiles. So which arm has the smallest quantile, or which arm has the largest, smallest conditional value at risk. So, those are some of the examples, but it's a very general framework. You just want to kind of, given a vector, you want to find out which partition it belongs to. So in this best arm setting, suppose you're given three arms, you sample from them, you look at the data, right? It comes from some distribution. You don't know the distribution. You just know the data. And now you want to decide when to stop. I mean, you want to figure out which arm has the largest mean, and you want to do it in the fastest possible manner. So we want to give, a theory behind what does all of this mean, and when can you do it, and when can you not do it. All right. So other problem which we'll think of, which is kind of geometrically very pleasing, is that, suppose I'm given two arms right here. Suppose their mean is M1 and M2. And suppose I'm given this hyperplane here. So I don't know on which side of the hyperplane this vector of mean lies. So the question I'm trying to answer while sampling from these arms is whether it lies in set A or whether it lies in say, set A complement, which side of hyperplane it lies. So this has a very pleasing kind of, answer. So it's worth looking at this. And many problems often are kind of, you're looking at union or intersection of hyperplanes. So it's a good way to start to understand how one comes up with answers. Other thing, as I just said, you could have a vector of arms and you want to say whether it lies inside the polytope or whether it lies outside the polytope, A or A complement. So, really what's going to happen is that this vector of probability distributions lies in some set. I don't know whether it lies in that set or not. I'm going to do all this data-driven calculations and decide and come up with a guess whether it lies in a particular set or not. So real question is, have I guessed correctly or not? So have I guessed the correct set AI, or have I instead landed up in AI complement? So it makes sense to reduce ourselves to just looking at two sets. Have I, this vector of distribution, does it lie in the correct set? Have I concluded that it lies in the correct set, or have I made a mistake? So that's why it's reasonable to just think of two sets, A and A complement, for much of the discussion. Okay, any questions so far?
When you talk about nu being a vector of distributions, collection of vector of distributions?
No, mu is a vector of distributions. Q is a collection of distributions.
Nu. I'm talking about this nu.
Yeah.
So the fact that it belongs to a probability distribution, is that going to play a role, or this theory seems to be general?
It's all about being able to sample from nu1 to nu_k. That's all I can do from nu1.
Okay.
I don't know anything else. I can just generate samples. So I have to guess these distributions.
Okay.
Right. Okay, so this is some settings. So what's the agenda?
So Sandeep, I had a question.
Yeah, go ahead, Siddharth.
So this mean that you've taken the means for different arms, are they the only statistic you can take, or you can take other statistics?
Any statistic you want. So we'll do, in this talk, we'll talk about quantiles and we'll talk about conditional value at risk. But you could take any general statistic. And this broadly, this theory will help you, that's where we want to go. So we want to have insight even in that setting.
Okay, I see. All right. Thanks.
Yeah, great. So far, later we specialize to means and CVARs and value at risk. And you'll see why one needs to do these things as we go along. So we develop a methodology for computing lower bounds on computational effort. So it's very nice that you can actually come up with a very crisp methodology that any algorithm which is going to be delta correct, if it's promised to you that it is delta correct, meaning it's going to make an error with at most pre-specified delta probability, it has to satisfy some lower bounds. You can't help it. And then that lower bound actually gives you a very crisp kind of max-min problem. So this involves exploiting the geometry of the problem structure, on which you can use duality and min-max theorem. So you can really understand the lower bound problem very well. And once you understand the lower bound problem very well, its structure, then you can use that to actually develop algorithms which match the lower bound. As delta goes to 0, the performance of the algorithm is as if you knew the lower bound. So the amount of effort you spend exactly matches the lower bound to the first order. And this involves exploiting the geometry of the problem structure. All right. So we'll develop this for in the half space problem which I mentioned, convex in the complement of convex set. This is places where things are, one can say some nice things easily because the geometry is nice and simple. So that's what we'll do. That's the agenda. And the results are first discussed for single parameter exponential family of distributions. So first of all, I'll just keep the distribution simple. So I'll assume that all my vector nu consist of probability distributions which can be represented by a single parameter. So in particular, the distributions mapping to the mean, it's 1 to 1. So I can just think of a distribution as a point in single dimension. So that would make my life much simpler. And later we'll discuss how to go beyond this, because we'll discuss that we need some restrictions, but how to go beyond to families like this. All the distributions whose 1 plus epsilon moment is bounded from with some constant b which is known to us. So there's a known bound on the 1 plus epsilon moment. So that's all we'll assume about all the distributions. In that world, what are the lower bounds and how do we come up with algorithms which match those lower bounds? And we'll also talk about tail measures, including C bar and bar. So that's our plan for today. But it is a toolkit, so there's a lot more that needs to be done. Okay, now let me not spend too much time on this, but I'll give you a flavor of what kind of literature there is. So these were called ranking and selection problems, these best arm problems, finding an arm which has the largest mean. So you want to rank them, for example, you want to find the best one, maybe you also want to rank them all in complete order. So these are all ranking and selection problems. Statistics, people have been thinking about this for a long time. So Chernoff had a seminal paper on this in 1959. His student Albert had another paper which took it much further in 1961. So a lot of good ideas go back to that time. Simulation people come up with this problem because this is inherent to simulation. You're given complicated simulation designs. You want to figure out, for example, say a road network, massive road networks. You have simulation models for each of these road networks. And you want to find out, okay, which amongst these road networks has the least congestion. So a lot of literature is in that world. I actually came on this problem from simulation first. Lately, last 2 decades, a lot of work in computer science, very high quality work. And I've actually not updated this list. There's a lot of new work that's happened since, but thousands of papers on these kinds of best arm problems. Okay, now we'll talk about optimal delta correct algorithms for partition identification problem. So what does that mean? So given a vector of k arms of probability distribution, and what's our algorithm? An algorithm is going to be an adaptive sampling strategy. So sequential adaptive sampling, you look at the data and decide which arm you're going to sample next, and you carry on as so on and so forth. And then there's a stopping time tau. So at some point you say, okay, I've seen enough. I have enough data. I'm going to draw a recommendation. So then you say, okay, this vector of distributions belong to one subset of the partition. See, that's the whole point in all of these things. We don't want to estimate these distributions. Estimating the distribution, boils down to some kind of central limit theorem. So that requires enormous amount of data. If you just want to figure out which partition it belongs to, that's a simpler problem. You can do it faster. So that's what we want to exploit. And we'll see that, our algorithms are computationally requiring order log 1 by delta computation effort. So which is much less than if we wanted to actually find the distribution. All right. An algorithm is said to be delta correct if for any set of distributions, mu1 through mu k, it announces in finite time tau that mu belongs to some set A of j, some partition A of j, with probability of error bounded by delta for all delta greater than 0. So if algorithm has these properties, then we say it's a delta correct algorithm. And because an algorithm has these properties, it has to satisfy some lower bounds. And that gives us a handle on a theory for these problems. So that's where we're going. So now the lower bound itself will rely on change of measure arguments, which go back at least to Lyon Robbins 1985, and probably earlier. People have been using change of measure arguments in hypothesis testing for a very long time, even before 1985. But in 1985, this was used in the bandits setting. But we'll specifically use an inequality for delta correct algorithm developed by Kaufman, Kaplan, and Garibay 2016. They crystallize, some results which are asymptotically known. They come up with a non-asymptotic inequality, and the flavor of the inequality is as follows. And this is worth kind of absorbing, because this is really the main crux of, which helps us out handling these kind of problems. So suppose mu lies in AI. I don't know that. So when a user is trying to decide which partition this mu lies in, they don't know which AI it lies in. But as a person who's analyzing this algorithm as an oracle, I know these things. So I know that mu lies in AI. I'm just trying to see what are the lower bounds which are inherent in this kind of, in delta correct algorithms in this framework. Now, suppose there's a nu which does not lie in AI. It lies in AI complement. See, your algorithm is going to see data, and it really has to decide whether the data is coming from mu or whether it's coming from nu. Because if it says it's coming from nu, then it's making a mistake. That probability has to be controlled. It has to be kept to less than delta. If it's coming from mu, you need to say that it's coming from mu with high probability. I mean, you need to be able to say that, yeah, with high probability. So where each arm I is pulled ni times, so suppose each arm I is pulled ni times, then the following inequality, the distribution separation inequality follows. So this is worth observing, that if you have a delta character algorithm, then it must be that if indeed the data is coming from the distributions mu, that the number of time ith arm is pulled for each I equal to 1 to k times this Kullback-Leibler distance, this separation between mu I and nu I, the smaller this is, all else being equal, larger this guy is going to be. So this is really saying that, okay, mu I and nu I are, if they're well separated, then I don't need to sample the arm I that much. If they're not well separated, then I need to sample the arm I lots of times. But this inequality has to be true. This summation on the left-hand side, that has better be greater than log 1 by delta. So this is the key inequality that Kaufman, Kappe, and Garaviel came up with. So any questions on this? So any delta algorithm will have to satisfy this inequality. And this is for every nu which is lying in A complement. Right? So that's what makes this interesting. Okay, so where do we go from here? So let's first understand why this inequality comes about. That's, that's perhaps insightful. So suppose we are given this data, because algorithms only observing data, right? It for ith arm, I from 1 to k, it observes nj number of samples, and then it decides. Right? These samples are adaptively generated by delta character algorithm. Then the algorithm will say if mu lies in AI, then probability under the probability measure mu that the algorithm looks at data X and says it belongs to AI, that must be at least 1 minus delta. Right? That's the claim of the algorithm. And for nu lying in AI complement, if the algorithm says that X belongs to AI, then it's saying something wrong. So that probability must be less than or equal to delta. Right? So now I don't know how many of you are very familiar with change of measure arguments, but these two probabilities here, they can be related to each other by change of measure, just by the likelihood ratio. So P nu indicate, this is just the expectation of the indicator that X, X leads to the conclusion AI. So I can express this under measure mu by just adding a radon-Nikodym derivative, d mu by d nu here. Sorry, d mu by d mu here. And for independent samples, that's just the product of the densities of the samples generated so far. And that's just this quantity right here. It's just a more complicated way of writing it. But this is just the product, because you see the exponential, you see the log, you see the minus sign. So it's really d mu a for each sample xaj that I've seen, for each arm A from 1 to k, and number of samples from j equal to 1 to n of a. So it's just the product of the densities. So product of the densities allow me to go from one probability measure to the other. So that's very nice. What do I do with all this? I need to, yeah. So what I do with all this is as follows. So now, if you are, if we are all friends here, and you kind of trust me as a person, then you say, okay, if I tell you that this indicator can be ignored, because now I've expressed everything under measure mu. Under measure mu, this indicator in any case has at least 1 minus delta probability. Right? So, let's just say that this delta, we can do some analysis and get rid of this indicator. Now, if I just apply, so this probability now becomes equal to this guy here. And now if I apply Jensen's, so I bring this inside here, right? Because exponential is a convex function, I'll simply get a lower bound, right? So this will have to be, once I bring this here, that will have to be less than or equal to delta. So that gives me this probability, this inequality right here. It just follows from here. So is the logic clear? So it's not that surprising. Any delta correct algorithm, by the guarantees that it's giving you, must satisfy this inequality. Any questions so far? So now we'll go ahead with this inequality. We'll assume that this, no, each arm has to be pulled these many times. This time the separation summation has to be getting equal to log 1 by delta. Very good. So now we can see a lot more since we have this. Okay. So now we want to get a lower bound on our computational effort. So this was the quantity, which depended on the algorithm. So let's just make it a variable. So Ti is the number of times I'm pulling arm I. So let's make it a variable, right? So this has to be true for every, So this guy needs to be true for every new in AI complement. I'm just keeping 1 here, log 1 by delta, I just normalized away. So I just called it 1. So this has to be true for every new. So I get, any questions? So I get lots of inequalities, right? So think of these as infinitely many inequalities. And amongst these, with these inequalities holding, I want to minimize summation Ti, right? This gives me a lower bound. The solution to this will be a lower bound to any delta correct algorithms effort. Because summation Ti is just number of times I'm pulling each of these arms. So it's the total number of times I'm pulling arms. It's the expected amount of computational effort. So any algorithm will have expected amount of computational effort, which will be lower bounded by this, right? So just from that one inequality, this follows, and I can do some more stuff here. I can just multiply and divide by summation Tj above and below here, right? So now minimizing this quantity is same as maximizing this quantity. And in this quantity, Ti upon summation Tj, that's just the weights in a simplex. So essentially my problem of finding a lower bound on the expected effort becomes this maximum problem right here. So, this guy right here goes in the denominator here, and I want to minimize this. So I want to minimize this whole thing, which is same as maximizing the denominator, which is basically solving this maximum problem. And 1 upon the solution to this gives me a lower bound on my expected effort. So let's just appreciate where we are right now. Let me again erase everything. So where we are right now is we are saying that expected amount of computational effort, I have a lower bound on that in this partition identification. And that expectation will be just inverse. So that lower bound will be just inverse of this quantity right here. And this quantity here is infimum over, so this is like a game going on. You as an algorithm designer chooses what fraction of time you're going to pull each arm, right? And once you pick this fraction, the nature adversary chooses your worst enemy, the new in your AI complement, which is the hardest to separate, right? I've decided that I'm going to pull my first arm maybe 5% of time, second arm 15% of time, so on and so forth. And then this infimum tells me that in that case, the most difficult arm to separate from the vector of arms mu is this new in AI complement, right? So now I just choose my weights in such a manner that I maximize this minimum. Right? So it's a game going on basically. So it's this nice maximum problem that I need to solve. So that's my lower bound. And that's really all there is to it. We came up with a problem which seemed like it's very complicated, but now it's just this lower bound. So what's an algorithm? Algorithm is going to be, okay, I generate some samples, right? I estimate my mu's from my samples. I somehow have an estimator from just empirical distributions, right? Then I saw with that empirical distribution plugged in instead of mu, I solve this maximum problem and come up with my W's. So to the extent that I have empirical distribution, which is close to 2 distributions, these W's by continuity, and that needs to be shown, is going to be close to 2 W's. And then I just chase those W's. I try to simulate in such a manner that I'm managing those, I'm kind of matching those fractions. So that's the idea, right? So this is nice, but sometimes this problem here can have a solution equal to 0. So it's not a very good lower bound then. It's telling you that sometimes, so 0 actually is, well, in this case just means that the problem is so difficult that you need infinite amount of computation effort. So let's at least identify when that happens and let's build conditions to rule that out, because then we can't do much. So some restrictions are necessary on distribution of underlying arms, right? So let's understand what those restrictions are. So restriction on underlying distribution. So consider 2 arms. So these are two probability distributions with mean M1, M2, M1 greater than M2. So this is, suppose a delta character algorithm is going to look at these two arms and it's going to compute, it's going to, after generating samples, conclude that, okay, arm 1 has the largest mean with at least probability 1 minus delta, right? Because it does have the largest mean. Now it has to make sure that, the data that it's seeing is not coming from another two arms, nu equal to mu1 and mu2, where this first arm is, this first arm is same as before, but now the second arm, nu2 is another distribution in the universe that I'm considering, whose mean is higher than M1. So when I see the data, it looks like it's coming from these two distributions, but I'm worried that it might actually be coming from these two distributions. So I want to see enough data so I'm comfortable that it's not coming from these two distributions, right? So let's go back and see what that means. This means if you go back to this inequality, which I showed you from Garavier and Kaufman, that because the first two arms are the same, in both the setups, this first arm is the same. So Kullback-Leibler between them is 0. So really all I get is that, if I have a delta correct algorithm, then expected times I pull arm 2 times its separation between mu2 and nu2, this must be greater than or equal to log 1 by delta, right? This just follows from the inequality which I motivated earlier, because it's a delta correct algorithm. This tells you then that this expectation must be greater than or equal to log 1 by delta into 1 upon this Kullback-Leibler mu2 nu2, but over all nu2, where mean M3 is bigger than M1, right? I need to be comfortable that this data that I'm seeing is not coming from any such, pair mu1 nu2 distribution, right? I need to be comfortable with this. Now this we can show that if the distributions are unbounded, this can be made arbitrarily small, and hence this will be actually infinite. Hence finite expected time algorithm is not feasible without further restrictions. So we need further restrictions. This is not going to work. Why do we see this? So this has a very nice intuitive content that, I can give you, suppose your underlying distribution was this green one right here. Now, what's a distribution which is difficult to separate from this green one? So think of this red distribution, which is basically green distribution, but with small amount of mass taken away from it. And that small amount of mass is put some point later, right? You choose this point carefully. Now, turns out that by doing this and by choosing this mass that you are transferring carefully and this point carefully, you could have two distributions which are arbitrarily close to each other in Kullback-Leibler distance and arbitrarily far in terms of their means, right? So they are going to be really difficult to separate. So, one distribution can have a much larger mean, but still be arbitrarily close in terms of Kullback-Leibler distance. So that's a problem that you can't get away from. So you don't want to have, these distributions, you can't say much about them. So some restrictions are going to be necessary in your space of distribution that you consider if you want to have good algorithms.
So Sandeep,
Yeah.
sorry, so these lower bounds that you are discussing, they hold for the algorithm being randomized as well, right? There is no distinction as such.
Absolutely. Absolutely.
Okay.
Yeah, no distinction at all.
Okay.
Right. So this is an issue now. So first thing we do, and this is, to illustrate ideas much, much more cleanly. And this was something which people had already studied, or they were studying. In this world of bandits, people were kind of obsessed with Bernoulli random variables to begin with. So these are one parameter family distributions. And then they said, okay, because it's just one parameter, it keeps things simple. Then a natural generalization was this one parameter exponential families. I won't describe the family here. For our purposes, there's no need for extra notation. Just that there's a single parameter describing a family, like, for example, for I guess binomial with number of successes or Bernoulli, number of trials fixed or Bernoulli distributions, Poisson, Gaussian with known variance, gamma distribution with known shape parameter. So these are some examples. There are more examples where there's just a single parameter that's missing. So distribution can be mapped to a single parameter, and distribution in particular can be mapped to the mean. So, without loss of generality, we can just think of means as representing the distribution. So this allows us to think of Kullback-Leibler divergence as a function of the means of the distribution. So now the argument for the Kullback-Leibler distribution is not going to be probability distribution, it'll just be the means. So that makes our life much, much simpler. So in much of the remaining talk, until I come to the heavy tail part, I'll assume that Q is a collection of vector of parameters in Rk. So all the sets which I showed you, because now vector of distributions can be represented by a vector of points in the Euclidean space. So my Q is now just a set in a Euclidean space. So that just makes the geometry much easier to appreciate. So in that world, what happens to the lower bound? That's the question we're going to ask right now. Right? In that world, suppose set A and A complement are half spaces. Can we say something more about the lower bound? Right? And the point is, once we can say a lot more about the lower bound, that makes it very easy to come up with the algorithm that actually matches the lower bound. All right. So this is where we are. Our A is this subspace here. So we assume that this subspace is given. So AIs are given. I equal to 1 to k summation AI mu I less than small b. That's my subspace A. And suppose for now that my mu belongs to this subspace. And now I want to know what do restrictions, what all the news in A complement in the other half space, what restrictions do they impose upon number of times each arm A must be sampled under mu? That's the question I'm going to try to answer now. Everybody with me so far? Any questions? So let's move on. Okay, so let's just keep everything in 2 dimensions. So this is our min-max maximum problem. Right? So let's understand this problem first. It's always good to have a picture to kind of clarify things. So let's assume that, let's just talk about the inner problem, this one here. So let's assume W1 and W2 are fixed. Now my mu1, mu2, without loss of generality, I'll just assume they're 0, 0. I'll just center everything around that point. Now we know that if nu1 and nu2 was also 0, 0, then Kullback-Leiber distance is going to be 0. Right? So this is going to be 0 here. So let's look at level sets of this function. I'll plot all the news where this function takes a constant value. That is going to be a convex set. So I'm going to assume, with this single parameter exponential family, typically what's going to happen is that these guys are going to be convex functions of nu1 and nu2. They will be convex functions. And what that means is that the level sets are going to be convex. So let's assume for now, in the Gaussian setting, for example, these level sets are going to be ellipses. So let's assume for now that this is the level set that I get. Right? And I keep on expanding the level set, or maybe I start from outside first. So I have this level set. This is all these points in the A complement set. I want to minimize this level. I want to have the minimum value of this level set, right? So I'll take this large ellipse and shrink it until I just touch A complement. And that's my answer for the inner optimization problem. So is this clear? Along with being a mathematician, I'm also a great artist, as you can see. So I make really nice pictures. I guess what I mean by that is that I can never make an ellipse if my life depended on it, but it's not too bad. So I have this ellipse right now. All these points on this ellipse are in A complement. Well, all these points right here are in A complement right now. So I want to minimize this, right? I want to solve this inhuman problem. So I shrink this ellipse until I come to this point. And this is the optimal solution for given W1 and W2. Now you can see, okay, now I'll modify W1 and W2 so as to get the largest value of this quantity right here. So maybe I'll do some gradient descent and achieve this. What you can also see is that, this as a function of W1, W2 is a concave function. So I'm maximizing a concave function with linear constraints. It's a nice concave convex programming problem. So I can do some kind of gradient descent on W1, W2 and converge to my optimal solution. So that it is solvable. I fix W1, W2, solve the problem through these ellipses. Then I find the gradient, I perturb my W1, W2, and so on and so forth. So that is going to work in this setting. But of course, in this setting, we can see a lot more. And what do we say here? So let's just see to this maximum problem here. What you observe is that A complement is a convex set. This function here is a concave function of W and convex function of nu. Right, so it satisfies this saddle point theorem, this science min-max theorem. Essentially, I'm taking infimum minimum of a concave function, right, and a maximum or a convex function. So just it's a the solution is going to be a saddle point. So you can imagine a saddle in your picture. So then whether you first minimize and then maximize the minimum, or you first maximize or minimize the maximum, you get the same answer. So what that means is that I can interchange the maximum and the minimum. Because of this nice convex on one side and concave on one side and convex on the other side problem. So that allows me to interchange the sign of the operation of maximum and minimum. So suppose I do this, then I get this problem, right? I've just interchanged the operation max and min. And now, you can see that this is easily solved, right? This is just linear in W. So I get basically at any nu in A complement, I look at the maximum of the Kullback-Leibler distances for each arm, look at the maximum, and I want to minimize that basically. That's how I solve this problem. So let's see what that means. Now, this is a very easy thing to see, and this graphic kind of nails it for you. So suppose my mu1 and mu2 are 0, 0. This is my A complement set. And suppose I'm looking at the Gaussian two arms with the variance 1. So my Kullback-Leibler mu I nu I is just nu I square upon 2. And suppose I start from some point in A complement, right? Nu1, nu2 in A complement. So I look at the maximum of these two, nu1 square by 2, nu2 square by 2. In this case, that turns out to be nu1 square by 2. So I reduce that. I want to minimize that, right? So this is my steepest descent direction. I carry on until I come to this point where nu1 is equal to nu2. And now the way to minimize the maximum is to go down this path until I come here. So that's my solution. And at that solution, there are two properties. Nu1 is equal to nu2, and they are on the border of the hyperplane. Right? So those are worth keeping in mind. Now this generalizes. So for more generally, optimal W star and nu star will have the property that Kullback-Leibler distance mu I nu I star and mu1 nu star is going to be equal for all I. So all the Kullback-Leibler distances are going to be equal. So this gives you an algorithm for solving these problems, and it'll be on the hyperplane, the nu I star. And plus, what are the Wi stars going to be? Recall that at the optimal point, the slope, it's the ellipse is tangential to the hyperplane. So there's a slope matching condition, and that tells you that it's a straightforward optimization calculation that this equation must also be true. Wi star upon ai into this derivative with respect to second argument, this must be all equal for all I. So with this, you go back, since all of these are equal, your lower bound, it turns out, is just going to be this guy right here. So inverse of this into log 1 by delta, your maximum solution is going to be just this Kullback-Leibler distance. You take inverse of that, multiply by log 1 by delta, and that gives you the lower bound on this problem, for this hyperplane problem. Right? So min-max is a very straightforward, simple solution, easy to see. Okay, so now I'll just change tax and tell you, okay, quickly, now that we've solved this lower bound, how do we devise an algorithm in this case? You give me a vector of distributions and you tell me which side of the hyperplane it lies on. How do I come up with an algorithm which is efficient? So what do I do? So we talk about, yes, go ahead.
So the fact that the worst nu lies on the boundary, right? That is intuitive, of course, because if it is on the boundary, then it is harder to separate. But maybe that is too harsh, because if it is on the boundary, what hope do we have?
No, I mean, mu is not on the boundary. So I'm assuming in all of this that mu is not on the boundary. So now your question is, okay, mu is close to boundary, but not on the boundary. What does that mean? That'll just mean that this distance, this guy here, the lower bound will increase. This KL between mu1 and nu1 star is going to be very close to 0 if mu1 and nu1 star are close to each other. But it's still a positive quantity, right? So that's still fine.
So the complexity is basically decided by this distance.
That's right. That's the other way. Yeah. And we'll exactly match this distance. So that's the nice thing about the sequential algorithm. If the problem is hard, it just takes longer to solve. The time tau when you stop just becomes much more. All right, so let's come up with the algorithm which matches this. So I should hurry up a bit, I guess. Okay, which arm to sample? So you'd want me to stop by 503 or something, right? Or earlier?
Yeah, 5 is fine.
5 is fine. Okay, so let me aim for 5 then. So decision which arm to sample and when to stop. So this is, closely follows the work by Garvier and Kaufman in the best arm setting in 2016. But let me just tell you what the essential idea is. It's not that great. At any sampling step n, ensure that at least root n samples are allocated to each arm. So you just make sure that you're not starving any arm. And you allowed sublinear errors. Sublinear, you can throw away a sample. It's okay. It doesn't affect the matching the lower bound up to the first order. Okay. So yeah, root n you can do, and then so you're not starved any arm. So now you got a mu hat n, which is not a terrible approximation to mu. Mu hat n is estimating the mean parameters and hence estimating the distribution. So because you've given enough samples, it's not a terrible approximation. So you have to prove this continuity, but the weights you come up with mu hat n are with high probability going to be the weights you come up with mu. So it's not a bad, so with large probability you're doing okay. So basically what you do is you chase these weights that you compute. You compute your empirical means, mu hat n's, plug them in the maximum problem, compute the W stars corresponding to mu hat n, and just chase them. Make sure that you're not too far from them. So that's the algorithm. The issue is when do you stop? So it's very good that you're doing, you're matching the weights which you should, which the lower bound is telling you to. When do you stop? So the stopping rule is as follows, and this is motivated by generalized likelihood ratio method, which goes back to Chernoff. It's used in hypothesis testing. So what you do is, at any iteration n, your mu hat n lies in some set A tilde, either it's A or it's A complement, we don't know. You find the maximum likelihood value with the data that you have, right? This mu hat n that you've got essentially is maximizing the likelihood value. So that becomes the numerator. And then you look at the alternate hypothesis. Let's look at all the nu in A tilde complement. What's the likelihood of those guys happening? And let's look at the ratio. As long as this ratio is small, you can't rule out the fact that this data might be coming from A tilde complement. Only if this ratio is large enough that you can rule that out with high probability. So that's what you do. You look at this ratio, and when this ratio is large enough, that's when you stop. That's a stopping rule. So more specifically, this ratio actually turns out to be exactly this. It's very interesting because it's very close to the lower bound problem that we saw. NIN upon n, we are chasing the W star, right? The weight. So mu hat n here, this quantity looks more and more like mu, and these guys look more and more like the weights because we are chasing them. So this looks very much like the lower bound problem. So you look at this quantity, and when this quantity is large enough, because this is exactly this quantity, when this quantity is large enough, that's when you stop. So what does it large enough mean? So, one needs to do some analysis for this, but basically you choose your threshold function as log C n upon delta. C is well chosen. And basically then your rule is after iteration n, if this quantity here is bigger than, I put n on the denominator. So if it's bigger than 1 upon n into beta and delta, that's when you stop. And now you need some kind of analysis. You need some kind of concentration inequalities to show that this guy is typically not going to take such a big large deviation. It will take large deviation only with small probabilities. So because we've chosen our beta and delta in a careful manner, stopping and making a wrong decision will not involve probability more than delta. So that's where the analysis goes now. You kind of do some concentration analysis for this distance and for this quantity, and then you argue that you'll stop in the wrong manner with probability at most delta. And that's how this whole thing works. Okay, so let's move on. So this is the kind of theorem that you prove, that tau delta denotes the stopping time, then expected value of tau delta divided by log 1 by delta. As delta goes to 0, asymptotically, is matching your lower bound. So you completed the story. It's a pretty good algorithm. This plug-in algorithm works very well. All right, so that's very good. Now characterizing the, so now let's just talk a little bit about more general settings. So suppose when A or A complement is convex, then what happens? Let me just take this. It seems very interesting. Hello? Yes, I'm giving a talk right now. If is somebody really sick? Otherwise, we can talk later. Are you calling the fourth time and you're calling a wrong number? Okay. Chalo. So when A complement is convex, so let's take the simple setting where mu belongs to A, but A complement is convex. So in that case, the thing is we can still do our our whole theory of saddle point still holds, so we can interchange max and min. So we do that. So we are really just solving this problem then. Maximum, maximum of all these Kullback divergences between arms. We look for a nu in a complement which minimizes this. But there's a very nice property we get. So there'll be a unique solution nu star and w star. W star need not be unique, but nu star is going to be unique. But this is a nice property. There exists a maximal set I, a subset I of the arms for which W star I is going to be 0. So you really need to only sample a subset of arms, not all the arms. The remaining guys you sample 0. In the optimal setting, you only sample a subset of arms, and those subset of arms at nu I star have the property that the separation across arms is constant, while the arms which you've ignored, they actually have separation which is less than the constant. So, the point is in this min-max problem, the W's are up to you. So you steer your W's in such a manner that you make the problem easy. So you just kind of get rid of the arms which are difficult to separate. I complement. So you give them no weight at all. And then the arms you do sample, you kind of, do some kind of load balancing and make sure that the Kullback libraries are equal for them. So that's the structure. So it's a nice kind of structure that comes out. But basically, in terms of algorithm, it's saying that quickly figure out which directions are not important and don't sample there. And not important meaning they're difficult. So don't sample there, but basically sample so that you can separate from a projection of a convex set. See, saying that mu does not belong to A complement, it suffices to say that a projection of these arms onto a smaller subset does not belong to a projection of the set A complement on a smaller space. So this is an illustrative example. Again, same as before. We start with this point right here. Now nu2 is higher, so we do steepest descent, and we come down to this point. At this point, if you want to minimize the maximum, you go on the line where the two are equal. But now you hit the boundary of the set. Now the descent direction which improves is right here. So you stop at this point. But the nice thing about this point is that at that point, nu2 is bigger than nu2 star is bigger than nu1 star, right? So what that means is that rather than separating this from this set, you should just separate arm2 from this region. Just sample arm2 and convince yourself that it doesn't belong to that region. Its mean is not that high. And with that, you can conclude that, okay, these two arms don't belong to A complement. So quick, in terms of actual sampling, you'll give root n number of samples to both the arms, and you quickly figure out that all you really need to do is separate in this direction. So you just focus all your effort on the second arm, and that's it. Okay, so algorithm when A complement is a union of half spaces. So let me just go a little quickly because I want to talk about heavy tails a little bit. So now I want to, well, it's the lower bound right now. So I want to figure out, okay, how to get the lower bound in this setting, how to calculate the min-max problem. So what I'll do is I'll fix my W's and I'll draw an ellipse, and I'll draw the largest ellipse which lies completely in A, or the smallest ellipse which just touches A complement. So, but basically for each plane, I can figure out how far I am from there because I can take each plane separately. So I'll just figure out how far I am from each one of them and just go the minimum distance with a given W. And then I'll perturb my W using some kind of stochastic approximation, some kind of stochastic gradient method, because I have a nice convex programming problem. And then I carry on. So I need to solve this min-max problem, max-min problem. For a given WA, I'll solve this problem. And this I can do by finding the nearest hyperplane. I'll just solve it for each of these hyperplanes. I'm not claiming that this is the fastest algorithm. but it's nice and intuitive at least. And then update WA using steepest descent and repeat. So that would be one algorithm to solve this problem. Okay, now let me quickly talk about what to do when we move away from this single parameter exponential distribution family and instead look at the family where the moments are bounded by 1 plus epsilon moments are bounded by some known B. So this is important that we know this B. All right. So recall that our lower bound continues to hold. That's unaffected by these things. So this is a lower bound now, where A complement again. So now I'm going to just look at the best arm setting, just to illustrate the ideas more cleanly. So now I'm saying that the best arm is arm 1, and I want to just solve my this lower bound problem. Essentially saying, what's the lower bound on expected number of times I should pull all the arms. So what is the alternative configurations? What constraints are they imposing? So this is my alternative set. All the vector of distributions, where the second, where the best first arm does not have the largest mean. So in reality, under mu, first arm has the largest mean. So in alternate configurations, it doesn't. Right. So I'm going to look at these. And what I'll do is, what's going to help me is defining this quantity right here, the KL inf eta x. So now eta is a probability distribution here, and x is a real number. And I'll take x to be greater than mean under eta, and I'll solve this optimization problem. So this is an optimization problem in the space of probability measures. So eta is fixed. I look at all the k's, just all the probability distributions which lie in L, meaning under which the 1 plus epsilon moment is bounded by B, and whose mean is greater than or equal to x. So, amongst all the distributions whose mean is greater than or equal to x and which satisfy my moment constraint, I'll find that distribution with the smallest Kullback-Leibler distance from eta. That's KL inf. And essentially what I'm going to do is, I'm going to, say that this problem here boils down to this problem right here. So I've basically taken KL distance between two probability distributions, mu A and mu A, and replaced it by KL inf between mu I, this is mu A, and xi. So I've, instead of having an infimum outside, I brought some of the infimum inside, where I've kept the means fixed at xi basically. So then I've kept the minimum Kullback-Leibler here. So now my D complement set is again in RD. So it's just all the Euclidean points where x1 is smaller than the other x's. So you can argue, it's not a difficult thing to argue, that my min-max problem, maximum problem now reduces to this problem. So maximum amongst all w's lying in a simplex, infimum or all x lying in this D complement, which is in Euclidean space as before. And now instead of KL between two distributions, I have KL inf. So in some sense, one just hopes that if we can replicate everything that we are doing with KL, now with this KL inf function, we are kind of done. Because we are really trying to separate mu from other distributions. So we are saying, let's keep the mean fixed and let's find the worst distribution that we have to worry about. And let's plug that in here and let's play with that. So result, and this takes a bit of technical effort, that KL inf eta x is convex and twice differentiable in x and jointly continuous in eta and x. So joint continuity is actually not so straightforward, because now you're saying that eta is, a probability distribution. So it's continuous in terms of the underlying probability distribution. So we use Levy's metric to measure distance between probability measures. So our analysis of lower bounds is similar to the earlier when with KL inf mu ix replacing KL mu I nu I in the single parameter exponential family. So everything goes through. So what happens to the algorithm now? So our earlier algorithm was that if empirical means are in A tilde, you look at this quantity here in the single parameter exponential family. If it becomes large enough, that's when you stop. Right? That's what our algorithm was. Now what we'll do is, similarly, we'll just compute this quantity right here. But now we have KL inf here. Right here. We have KL inf in this place as opposed to KL before. Right? So there are all kinds of issues of how easy it is to compute KL inf and all of that. But conceptually, at least, let's assume that's not a big issue. The other issue is, an interesting point to keep in mind is that empirical distribution that our data generates, although the true distribution lies in L, will satisfy this moment constraint, the empirical distribution may not, with some probability. So one has to worry about that as well. Now you want to show that you won't make mistakes with this. That chance that you end up making a wrong decision is not going to be happen with large probability. So to do that, to come up with a supporting analysis to show that the algorithm that you have works, you need to develop some kind of concentration inequalities for this function right here. So this is empirical distribution corresponding to underlying distribution kappa. This is the true mean of the empirical distribution. So if the true mean was m of k and we had to put true distribution kappa here, then KL int will be 0. But now we are saying that now instead of the true distribution, we are putting an empirical distribution. What's the chance that we see a deviation? So we want to be able to say that this probability of this deviation, this large deviation, is bounded, and one can actually come up with explicit bounds which are exponentially decaying with u. So a lot of work goes into coming up with these kind of concentration inequalities and then coming up with concentration inequalities for this quantity right here. So all of that needs to be done. Once you do that, you can come up with the same kind of theorems. And what helps you do all this analysis is using the duality, basically, that my KL inf problem was on the space of probability measures, but the dual turns out to be a problem on a parametric space. So I'm looking for two variables, lambda1 and lambda2. So I'm maximizing over that. E of eta into this function here, with lambda1 and lambda2 are variables. So dual is in the space of parameters. So that helps. So with empirical distribution, you look at the dual and then you kind of argue that dual is not going to take large deviations. So a lot of interesting duality ideas become useful in coming up with these kind of bounds. Okay, so very quickly, maybe in a minute, what do we do when we have tail risk measures? So we still are going to assume this constraint, because without this constraint, we saw earlier that we can't get a lower bound. Lower bound is infinite. So given confidence level pi, so var value at risk, or v pi eta for any distribution, is the pieth quantile for a given distribution. So it's that number, so that the chance of the random variable being either that number has probability at most pi, say 5% or something. And C bar at confidence level pi measures the average loss, condition on loss being greater than or equal to value at risk at pi. So given that you exceed this quantile, what's the condition on that? What's the expected loss? So that's given by C bar. These are interesting, because these are very applicable, particularly in the industries like finance and insurance. These are, people always say that, okay, I have this portfolio of all these instruments. Give me one number for what is the risk of the portfolio. And one number that became popular was value at risk. Well, how much money is at risk at 1% level or at 0.1% level? So that was value at risk. And then people found that, okay, value at risk, while it's a good number, it has a lot of intuitive field, it has some drawbacks. So it's not a coherent measure of risk. But C bar is coherent risk measure. Coherent means that there are some axioms that risk should satisfy. It can't be that if I break up a company into two, then I get a more secure, then I'm in a less risky situation than if I had two companies together, because that would then just suggest that everyone should break up for risk management purposes. So coherent risk measures have these kind of axioms, and C bar satisfies them, bar does not. So now you can say, okay, given these number of distributions, find a distribution which has the smallest C bar or smallest bar. So one can do a lot of interesting analysis. My time is up. So what do you suggest, Ketan? Should I stop here? Or if you want to give me a minute or two, I can talk a little bit more.
Sure, please complete whenever.
Sure. Okay, so I'll just take a couple of more minutes. So for a distribution single parameter exponential family, one can actually show that V pi eta, C pi eta, like the mean, are increasing functions of the parameter. So in that setting, finding the arm which has the smallest value at risk is same as finding an arm which has the smallest mean. So all, it's still back to the best arm largest mean identification problem. So nothing new to be said in that setting. What becomes interesting is when you have, when you're not in the single parameter exponential family, when you belong to this bigger family L that we've been talking about, where you have these moments have a constraint, and now this becomes the alternate set. We're looking at, again, the maximum problem as before, but now we're looking, our alternate set is all the vector of arms, where the wrong arm now has the I guess I've written it a little wrongly. It should be the other way around, where the wrong arm has the small, so there should be minimum here. Because when you're dealing with C bar, you want to look for arms with the smallest C bar. So in this case, wrong arm has the smallest C bar. So you do the same thing as before. You again come up with this KL_INF kind of representation. But now the KL_INF problem is different. Now the constraints are no longer that your mean should be greater than equal to xi. The constraints are more like your C bar should be less than equal to xi, or C bar should be greater than equal to xi. So you have two directions. When you want to, when this xi is greater than the true C bar, or when the xi is, so this is the case when, it's greater than the true C bar, and this is the case where it's lower than the true C bar. So this is your optimization problem. When this x is more than the C bar under eta, so your kappa, you're looking for all the distribution with higher C bar than under eta. And this is where you're looking at new distributions which have lower C bar than eta. So this is low and this is upper, above. It's interesting because one of them turns out to be convex in X, the other one turns out to be non-convex in X. So that gives rise to its own set of technicalities. So otherwise you carry on as before. So one can show that this is going to be convex in L, because again, it's like in linear programming, in convex programming, the constraint is in the right direction. But in this case, the constraint is in the opposite direction. So this is not going to be convex. Remaining analysis is similar. Again, duality is used to arrive at concentration inequalities for the two KLMs. So that's where a lot of analysis goes in. Showing continuity of weights of the underlying distribution poses technical challenges. Value at risk is somewhat of a much easier problem. So let me not talk about this. Let me just say one picture, then I can stop. So if I want to find, this is my distribution, and now I want to find, this has a, say, value at risk at this quantile. And now I want to find another distribution with value at risk, same value at risk at this point. Right? The closest distribution with this. So what I'll do is I'll just take some mass from here, bring it down, and increase the mass here. So earlier, my mass with the old distribution here was a given pi. So I'll increase this mass here. So this mass is again pi. And this mass, I've taken the mass away here. So this is again 1 minus pi. So it's that simple. So you just, there's a lot of convexity that helps you solve this problem. All right, so that's all I had to say. I've taken too much of your time. Thank you. So we consider the pure exploration multi-arm bandit problem in general unifying framework. This involved finding the correct partition for a vector of distributions from a superset of such collections. We developed geometric and duality-based methodology for computing lower bound on computation effort for delta correct algorithms. Using these, we developed algorithms with matching computational bounds, and then we extended to heavy tail distribution and to tail-based. Thank you so much.
Thanks a lot, Sandeep. Very interesting tools for analysis of lower bounds. Actually reminiscent of the lower bounds derived for algorithms. The same approaches are often used.
I see.
Yeah, any comments on the difficult cases for which the lower bounds you don't have lower bounds, like the non-convex A complement case?
See, this max-min problem, of course, is generic. That's going to hold always. Now, you could say, okay, when does this max-min problem become zero? So in the sense that the problem is very easy in that case, or whenever this max-min problem is, when it's zero, then the computation effort has a bound of infinite. So then the problem is extremely difficult. But I think your point is more that let's assume that this maximum problem has a finite value. And where is the how difficult is it to solve this problem, where all these non-convexities come up? So my guess, and your point is, okay, so for example, in C bar, things became very difficult for us because you had non-convexities in one direction. VAR, things were quite straightforward. Means also was very simple, actually. It just turned out to be a convex programming problem. So we got lucky. So I don't have more to say on this. I think it's an interesting question and interesting things to look for. So performance measure where indeed things become much harder and you need non-convex methods to solve it. And that's really it. If you can solve this lower bound problem, then plug and play algorithm will work. The only thing is going to be with plug and play algorithm to prove that they are delta correct. That's again going to be very difficult. When you have non-convexity, you have to prove this concentration inequality. So,
and actually, that brings me to the second question. Like for the difficult cases, maybe if we apply those algorithms, we will get some upper bounds. So have you tried those, or have you obtained any of those?
I mean,
just be some upper bounds.
I mean, it could well be that the algorithm that this is suggesting are actually the best ones.
Yeah.
It's just proving that they have a particular property is hard. It may well be that they have the property, but can you prove it?
Yeah.
So in that sense, it's an interesting problem that you have a good algorithm. Now, let me just say one more thing, because you asked me what is difficult here. So, one can turn this problem around and say that I'm not going to sequentially sample until I stop and I'm convinced that this vector belongs to a particular partition. Rather, I say that I'm going to just a fixed number of samples. You've given me a budget of 5,000 samples. I actually decide how to allocate them, right? Then how do I do things? Turns out in that case also you can come up with a lower bound, but there's no, and you can come up with good algorithm, but there's no proof that the algorithm actually matches the lower bound. And the thinking is that the algorithm does not match the lower bound. But then what does that mean? That's still a very open area. So it's an interesting area to think further about. But non-trivial stuff, without good people have thought about this, not gotten anywhere.
Okay, great. Thanks. Any other questions? Yeah.
Yeah, hi Sandeep. So I was just wondering, in this upper bound that you have,
Mm-hmm.
how much of it is necessarily sequential? Like the initial exploration part is completely parallel. You don't mind that.
Mm-hmm.
And even then, like I just like in general, how much of it can be parallelized, or does it like is it necessarily inherently sequential?
Oh, I see, I see. Oh, that's a good question. So yeah, in fact, Shubhadda and I, in our work for best term mean problem, we said that you can sample in batches, because I guess the point with parallelization is that, you have to update the weights that you're chasing, right?
Yeah.
So if you parallelize, then that updation is not happening immediately.
Yes. Yes.
And then you're generating a lot of samples, and then you're computing weights, and then you're. So yeah, you can go a long way in parallelization without suffering.
Okay. Okay.
So yeah, that's a good point, that these things actually can be parallelized without really losing the property that you're more or less matching the lower bound.
I see. I see. So, and do you see like an interpolation between this bandit setting and the multiplicative weight setting? Like, I guess you pull k arms at once. Like,
Yeah,
I guess the multiplicative weight would be pulling all the arms at once. Here you are pulling one arm, as you said, but you said that this can be parallelized a lot.
right. I mean, as such, multiplicative weight algorithms are used in the adversarial bandit setting. So here I'm assuming that underlying bandits are coming from a probability distribution of these samples. But if you assume that they're actually coming through an adversary, then you have these multiplicated arms, as you're saying, in the expert setting, where you pull all arms together. But there are versions of this expert setting to bandit setting as well, where you pull sequentially. So that works out, but that's literature that's more, that's more relevant to the adversarial bandit setting.
I see. Okay.
But there's very nice literature. There is good papers for you to see where you say, okay, I don't know whether I'm in the adversarial setting or whether I'm in a stochastic setting. So now, can I have a unified algorithm which kind of figures out from data first, whether it's adversarial or stochastic, and then follows accordingly adversarial kind of algorithm, which is this multiplicative weight, or this stochastic kind of algorithm. So very nice algorithm which perform equally well in both the settings.
I see. Okay.
Okay, thanks. Any other questions from the audience? Okay, so if there are no more questions, let us thank the speaker. So thanks, Sandeep.
Thank you. It's been very nice. I don't know, how bad is it to hear a non-live person? Is it almost the same thing now that you experienced many talks? I guess it depends on the talk.
Yeah, no, your talk was very good.
Okay, no, I'm just remembering that it's not live. I mean, not in front of the audience.
Yeah.
Thank you so much.
Thanks, Sandeep. So now
Yeah.
I will end.
Sure.
Thanks again. So bye. See you.
Bye.